whenever you
Fortunately
want.
enough, my heart is working quite normally, because otherwise, with all this.
Okay, so good afternoon, everyone. I'm glad to introduce Emanuele Macrì, who will speak about Hyperkähler manifolds and Lagrangian fibrations. Emanuele, please go ahead.
All right. So again, thank you for having me here and for the opportunity of presenting this talk. And well, yeah, okay. Let me say one thing, just one thing. So I guess the first time I was in the office with Claudio, I think the first thing we talked when I started in my undergraduate thesis was about two topics. I think the first time was the Liouville-Arnold theorem for interval systems and Hyperkähler manifolds. And so, but when I prepared these talks, somehow I was somehow amused that is essentially the subject of my talk of today, 21 years after. So anyway, so I hope that we'll see. All right, great. So let's start. So I prepared some sort of a colloquium style talk, but if you want more details or something, let me know. I'll try to speed up a bit for the time. So what I'm going to talk about, so it's about Hyperkähler manifold in this, and Lagrangian fibrations. So for those of you who comes from mathematical physics, these are just interval systems, okay, finite dimensional, and everything is over the complex numbers, okay. So it's a complex interval systems, but the difference that we look here is from the algebraic viewpoint. So I want them to be compact, okay. So let me start. So I will denote always by X. I hope you can see. A compact, complex manifold. So this means something which looks locally some open subset inside Cn, finite dimensional, with holomorphic transition functions. Okay. So let me assume everything is algebraic. So I'm using Chau's theorem. And so let me assume that X comes with a closed embedding inside PNC. Okay, inside the projective n-dimensional projective space, I'm asking that X is a closed submanifold inside, and so by Chau's theorem, for some miracle, that this is algebraic. Okay, so this is given actually by polynomial equations. More generally, I can ask something about a metric, and so I could ask that X carries an Hyperkähler metric, sorry, Kähler metric for the moment. We won't need the analytic, some of the analytic part is all behind this thing, but we won't need, so this situation will be enough for us. Although we'll comment a bit about this later. Anyway, so great. So that's what I'm assuming. And so the basic definition is the following. So definition, I'm saying that X is a so-called irreducible holomorphic symplectic. And in general, you do use the terminology Hyperkähler, although again, so this will mean that it admits an Hyperkähler metric. But as I said, we never use the metric explicitly sometimes in the yes. So if the following condition holds, so what I want topologically to be the smallest possible. So I will want X to be simply connected. We already saw some talks about Ugo spoke about this. And the second thing I want it that there exists a unique holomorphic symplectic form, which I generally call it eta, and of course unique up to constants. Okay, so I want something which is a symplectic manifold but over the complex numbers, and I want it to be as small as possible. So there is just one symplectic form up to constants, and the topology the smallest possible, so it's simply connected. Okay, and so this forces, for example, since the symplectic holomorphic symplectic, so I really want a symplectic. So this forces the dimension to be even, and I will denote it by 2n. Okay, so again, let me stress that we are looking at compact manifolds. Okay, so the theory of Hyperkähler manifold has a beautiful counterpart in the non-compact case. For example, Boychin system, for example, the model of X bundles. So we won't deal with this in this talk. Okay, this is interesting from several viewpoints. I think we saw some of the talk motivating a bit. So the first thing, okay, indeed, there is this viewpoint from the metric. So this comes from Yau's theorem, or better, Yau's solution of Calabi's conjecture. It's interesting from the viewpoint of holonomy groups. This comes from Berger classification. It's interesting from the viewpoint of the composition theorem, which is actually one of the motivation in algebraically to study these objects, is that if you want to classify things which have a trivial canonical bundle, let's say, there is always an étale cover, which this guy splits in 3 types of manifolds, abelian varieties, proper Calabi-Yau if you want something with trivial canonical bundle, and a Hyperkähler manifold. Okay, so this is one of the building blocks that we are looking at. Great, and so the question 1, which is the main thing which is open, is we want to classify this. So I want to classify compact. Let me test again. And I will use the word Hyperkähler because it's quicker, and somehow by some abuse of terminology, that's what has been used. So I want to classify compact, Hyperkähler manifolds. Okay, so that's a basic question. Okay, of course, it's very hard. Okay, so it's but something is known. Okay, and so we'll see that this is fine in dimension 2. This is a beautiful theorem by Kodaira, which I will talk in a second. And so the upshot of this talk is that I want to say something in dimension 4. Okay, so it's the next dimension where we are interested in. Okay, and so that's the result. That's the main result of that I'm going to present. Okay, so let me start with dimension 2. Okay, just for doing since we already saw something about this, so let me be slightly quicker. So dimension 2 are called K3 surfaces. So this was studied in the literature quite a bit. So this is the case n equal to 1. So a Hyperkähler manifold in dimension 2, so n equal to 1 in this case, it's called a K3 surface. And so there is one example standard of K3, which is the quartic, right? So this is, I take S. So this is a complex manifold, which comes with an embedding inside P3, okay? And is defined by a polynomial, as I said, that everything is algebraic, of degree 4. So this is the 0 locus of a polynomial of degree 4 in 4 variables, which is homogeneous, okay? So this is smooth, This is everything is smooth, and since the closed inside the compact is compact. Okay, and so 2 things. This is standard theory that S is simply connected. This comes from originally from Lefschetz hyperplane theorem, but actually this is actually, if you want, this is via Morse theory. So this is slightly more refined statement. I think the statement written like this we need for fundamental groups, and so this I think was. I think the theorem of Lefschetz was refined by Andreotti and Frenkel, and then by René Thom, and I think the last statement, which is due to Bott, I think. Okay, so it's simply connected, so that's great. And then it has a symplectic form. In this case, it's not so hard to find symplectic form. It's just coming from the residue theorem. Okay, so this is a Poincaré residue theorem that is telling you that if I take, I can write it if you want. Just for once. So it's the sum, but just write it just for fun. The sum of xi dx0 wedge dxi removed wedge dx4. Sorry, too many variables. dx3 divided by the equation f. F is the equation of the f is equal to 0 is the equation of our quartic. Okay. Anyway, so that's an example. And so what it means the classification? So the classification in this case is the following, as this theorem, as I said, by Kodaira from I think 1964. And the theorem says the following thing, that topologically, which a priori is not obvious somehow, the definition is just an abstract definition. This is an example. Not all K3 surfaces are quartics, but they are all deformation equivalent. So all K3 surfaces are deformation equivalent. And here, actually, if I want them to be in the same family with a connected basis, I need to also look at non-projective, but anyway, this is not super important. So deformation equivalent for us here means that I can put them in a family over some base, which, as I said, might not be might not be reducible a priori if I want a projective. And in which all of them are smooth, okay? I don't want to go into anything singular. And one element is a quartic, and another fiber is any K3 surface. Okay, so that's the statement of Kodaira. And the proof of theorem Kodaira is interesting. So there are well, the first thing is it was the theory of deformations that actually works very well just without any modification for Hyperkähler. So that's the first thing. So deformation, from the viewpoint of deformation, K3 surfaces are very nice. Namely, I can deform as I want. Okay, so said in other terms, the deformation space is smooth. The Kuranishi space is smooth. And that's the same for Hyperkähler. Okay, so that's the first thing. And so the idea is the following: is that I take a K3 surface, I deform it, and I hope for the best that if in this family, at least in this local family, I find a quartic. Okay. And surprisingly enough, this is possible because being a quartic is so-called a numerical property. So I can check if something is a quartic just by looking at divisors. So it's at subvariety of the codimension 1. That's not quite the proof how Kodaira did. That's a more modern proof. The proof of Kodaira was something more involved. He's used actually lagrangian fibrations. And so let me try to explain what a lagrangian fibration is in this context, and then let me try to generalize to Hyperkähler. So the statement we are aiming at is something of this form, that at least somehow we can classify Hyperkähler somehow maybe up to deformations. Okay, that's the first thing we want to do. Okay, so let's try to do an example, since we have still some time. So for example, what does it mean to deform a quartic polynomial? Okay, so deform a quartic simply means that I can vary the coefficients. Okay, and so I can vary the coefficient in such a way that, for example, I found a line. Okay, so that's a classical example. So I can vary the coefficients of my equation f such that there exists a line contained into S. And so if you want an explicit equation, and here it is, for example, I can choose the standard x0 to the fourth minus x1 to the fourth plus x2 to the fourth minus x3 to the fourth. Okay, equal to 0. And the lines are, well, they are there. For example, just to put a minus sign just for fun, because at least we see the lines. So one is x0 equal to x1 and x2 equal to x3. Okay, so this is two equations in T3. So this defines a line for us, okay, which is contained inside F. And so once I have a line inside, what can we do? Well, I can just draw the following thing. Let me just draw a picture. So I have my K3 surface here. I have my line here. This is my line. And so what can I do? I can just take a point on the surface, and I can take another line out of it. And so what I do, I just take the plane generated by the point and the line, and this thing is going to, sorry, that's not a good picture. Let me just do it slightly better. So this thing will define a plane, and this plane will intersect a new line, which I call it L prime, in a point. Okay, so this is the point P. This is the point, sorry, let me just change the notation. This is point pi of P. Okay, and so this construction actually does work. And so what is the fiber of this morphism? So the fiber is, so I have a quartic, I'm taking a line, I'm intersecting with a plane. So this means I get a curve of degree 4, but there is a line here. So what is left is a curve of degree 3, which is planar. And so a curve of degree 3, well, inside P2, this is a torus. This is a one-dimensional torus, namely an elliptic curve. Okay, and so what we get a morphism pi from S into P1. Well, a priori, you can complain that what happens on the line, but on the line is still fine. I can extend this morphism, although it's if the point's on the line, that's okay. And with fibers, which are planar cubic curves. Namely, these are tori. This is tori. one dimension. Okay. So what I have, they might be singular, of course. So what I realized that S as an integral system over with base P1, and somehow the idea is that so this is a so-called a Lagrangian vibration, because because if you want just by dimensional reason in this case, if I take a symplectic form and I restrict it to one-dimensional thing is 0. Okay, so what it means to be Lagrangian. Okay, great. So in some sense, Kodaira's theorem goes via this kind of thing. So these things they appear quite a lot actually. And the key point here is that you can realize when something is a Lagrangian vibration, it's an elliptic vibration, just numerically. Okay, so that's the key point here. Okay, great. And so that's what we want to do in higher dimension. Okay. And so the first thing is that, well, the first conjecture, which is the basic conjecture if you want to classify, is, well, this is true also for Hyperkähler. Okay, so a priori, we don't know that Hyperkähler in general, they will never be hypersurfaces. So that will complicate a bit the situation. But still, I can still say that this situation I just said is true. And so this is the first conjecture. This is one of the main conjecture in Hyperkähler, in compact Hyperkähler. So any compact Hyperkähler manifold can be deformed in exactly the same sense to a Hyperkähler manifold, still compact. Everything is compact. I won't repeat it. I won't repeat it anymore. Admitting a Lagrangian vibration. Oops. So I will be a bit more precise what you mean a Lagrangian vibration in a second. But that's what I will want. Okay, so if I want to start any classification, that's the first thing. If I have something which is Lagrangian vibration, it's slightly easier to start in general. Okay, so that's the idea. And so this is the first conjecture. And the second question that one can ask is that, okay, even assuming this conjecture, can I say something about the classification? So can one use this conjecture to say something about classification? In some sense, in a similar way to what Kodaira did, in some sense, in this paper. Okay, and so let's try. Okay, so that's a conjecture. So let's try to study a bit more this conjecture. This is too vague to be proven somehow. So I need a precise form of this conjecture. So let me say briefly what a Lagrangian vibration is now. Although it is you won't need so much this introduction. So Lagrangian vibration is an integral system. So how do I do that? So let me say briefly. So this is so pi from x into a base. So I'll be slightly technical here, but just for a second. So here what I want the base to be half dimension. I want the fiber to have the property that the restriction of the symplectic form to vanish there. Okay, so the fiber at least generically will be smooth, and so the generic fiber will be a Lagrangian submanifold. Okay, so that's the thing we want. And but there is some theorem that says that Hyperkähler manifold, the compact Hyperkähler, are very rigid. So if I ask that there is a morphism from a Hyperkähler manifold into something which is of lower dimension, and I want the fiber to be connected, then it must be a Lagrangian vibration. Okay, so that's the first thing. And second, well, of course, the version of Arnold-Liouville theorem says that Lagrangian vibration, under this condition, the fibers will be a billion varieties. So a priori, they're just complex tori. Okay, here X is projective, but this is actually true in general. So whenever I have something, the fiber will always be projective and the base will always be projective. So that's something that is interesting to observe. Anyway, so let me start with Lagrangian vibration. There is also a theorem of Matsushita that say also that even the singular fiber are not so bad. So the condition of being Hyperkähler guarantees that also the singular fiber, they have the same dimension, for example. And if you pick a point which is smooth on a singular fiber, this is also carrying somehow, is also Lagrangian at that point. Okay, so that's actually a very rigid picture. Okay, so the condition of being the Hyperkähler for X is very strong. Okay, so let's start to studying it. So the first thing I want to do, how do I study? I look at the second cohomology group. That's the first gadget that we have. And since X is simply connected by the universal coefficient theorem, this guy is torsion-free. Finitely generated abelian group. Okay, so it's finite rank, and it comes with a cup product. So any alpha in H2, I can just take the integral over X of the maximum I can take, which is to the power 2n, the cup product, and this guy is going to give me a number, which I call it C. This is the self-intersection. Okay, so the first thing is that I start with Lagrangian fibration, so what can I do? So the first thing is that B is projective. A priori, B is not smooth, but we won't worry about this so for the moment. And so it's dimension n. Is always projective, but in this case for us, X is projective, so that's not surprising. So in particular, I can find a class, which I call it alpha B, in the second cohomology of B, again with Z coefficient, which is the class of, if you want, a very ample, an ample divisor. So what does it mean, an ample divisor? It means I just take an hyperplane and I just cut it. Okay, so that's what it is. And so what I can do, I can take the pullback of this class. And so I get a class alpha, which is the pullback of this alpha B, which is a class in the H2 of XZ. And this is some algebraic class. So which are the properties of this alpha? This alpha is algebraic, as I said. So algebraic, this means that it comes from some subvariety of dimension 1, okay, of dimension 1. It's non-zero, because when I pull back something which is ample, this thing will be non-zero. Actually, it's very precise what I get. And the property that I get is something, okay, there is something very strong. I get the power n+1 of this class is 0, actually. But in this case, the only thing I care is that if I take the integral of alpha to the n, well, I can move a fiber, right? And so this means that this guy will be 0. Okay. And the third condition is slightly more technical, but if I take a curve inside X, so this is a closed curve, then what happens, I can take the integral over C of this class alpha. So this is a complex curve. So this is, again, is an integer. And well, what happens, if the curve is in the fiber, it's going to 0. So this number is 0. The curve is not on the fiber, will go down to a curve in B, and the intersection with an ample, with an hyperplane will always be positive. So this number is always positive. Okay. And this we will say that A alpha is nef. So the definition of something being nef is a class which is algebraic with a property that intersect positively all curves. All right. So that's the thing that I can handle. And now the conjecture, which is the precise version of the conjecture I stated before, says the following thing, that these three conditions that I just wrote are actually sufficient to find, they are necessary for having a Lagrangian fibration, but they're actually sufficient. And so here's the conjecture. So the conjecture comes with several names, actually. So this generally is called the Strominger-Riaud-Zaslov conjecture for Hyperkähler. And this is the name given by Verbitsky because he didn't know how to name it differently. But in algebraic geometry, this is a particular case of a celebrated conjecture, which is the abundance conjecture for Hyperkähler. So I will explain a bit why. And generally, sometimes it comes with the name of whoever presented it in the literature, which are Turing and Bogomolov, I think, originally, and then Hasse-Schinkel, and then Heuberg-Sovon. Okay, so this comes with a lot of names, this conjecture, and says exactly what I told you, that these three conditions are sufficient. So if I have X, a compact Hyperkähler, dimension of X equal to 2n, and then you assume that there exists an algebraic class alpha in the Néron-Severi, so in this case, I can say in H2XZ, such that alpha is non-zero, alpha is nef, and the degree of alpha, oops, is equal to 0, then the statement is that then there exists Lagrangian vibration. With a property, so f from x into b, such that if I pull back some ample from B, actually there is only one class of an ample divisor. That's another theorem of Matsushita. This is going to be equal to alpha, at least up to multiples. There is a conjecture also which multiple, but anyway, let's say alpha for the moment. Okay, so that's a conjecture. Okay, so again, this comes from some famous conjecture in the, and this is really for Hyperkähler is really the most important things that one has to solve it. To at least be able to say something about classification. All right, so that's the first thing, and I'll give some example of Hyperkähler in a second. But okay, so this is true for K3 surfaces. Okay, there are 4 known examples of deformation family of Hyperkähler known at the moment. There are 2 standard families, which are deformation of Hilbert scheme. I will talk about this. Deformation of generalized Kummer manifolds. And then 2 exceptional examples by O'Grady, which are OG6 and OG10, they're generally called. For all these examples, this conjecture holds in the strongest possible form. Okay, so that's something that so it's at least it holds in all examples possible. Let's say like this, but it's not enough, of course. All right, great. And second thing I want to say is that okay, for some of you that knows abundance. So abundance only gives us a morphism, but by what I told you before, whenever I have a morphism, then by this theorem of Matsushita, it's a Lagrangian vibration. Okay, so that's the first thing. There is another question here. I didn't say anything about the base. So what is the base? And again, this is somehow surprising, but the base it's very rigid. So again, being a Hyperkähler, the base is forced to be as nice as possible. And so the conjecture, again, there is a conjecture, which is the base is always Pn. So it's really the easiest possible variety for the base. So there is a lot of things known about this conjecture. So it's known to be true if we know the base is smooth. That's a fantastic result by Wang, fairly recent. Okay, so this is okay if the base is smooth, which is already somehow surprising. Okay, so you imagine I give you a compact Kähler manifold. There's only the fact that it's a Hyperkähler, so very rigid. If you have a morphism, it must map into Pn. Okay, so that's sort of surprising. And the second thing, is true for K3 surfaces. Well, that's okay. There is nothing surprising there. But it's the interesting thing is that it's true in n equal to 2. Okay, and this is work by Huybrechts and Chen-Yang Zhu. It's non-trivial, the proof here. So the proof is that if something is singular, they use minimal model program techniques to show that this cannot happen. Okay, so that's the case. And this we use this result. So in dimension 4, if you have a Lagrangian vibration, it is known that the base must be P2. Okay. Actually, knowing that if it's smooth is P2 is not so hard to prove, but the hard thing is to prove that it's non-singular. That is, sorry, it's not singular. It's not singular. Okay, great. So that's a conjecture. Okay, so I hope that this is clear as a statement. So the conjecture in Soldoni says that if I want to detect a Lagrangian vibration, so if I want to try to an argument a Lakodaira, then it's fine because I can do it at least numerically. Okay, so this is a purely numerical condition. Don't get too confused by the condition of being nef. That's you can always assume that's the case. That's a theorem of Huybrechts that you can do that. So anyway, so the moral of the story is that you want to check this conjecture. That's a key point. All right, great. And so something about the fibers. Sorry, before I go further. So as I told you, for a general point, the fiber by Liouville-Arnold, it's a torus. Okay. And so, okay, the variety is projective. Well, if it's a torus, I can try to look at if these tori come with a natural polarization as well. So how do I state it? So if X is projective in this case, then I know that there exists another class, which is algebraic, which I call it beta, which again in the H2xz, which induces a very ample, if you want, an ample class on the fibers. Okay, so the fibers are abelian varieties, so are tori, and I look at an ample class, and then by standard theorem in complex analysis, this is classified in some sense, okay, by some linear algebra over Z. But anyway, the moral of the story is that one of the elements which is interesting for us is the following number, which I call it A, which is defined as 1 over n factorial times the integral over x of alpha to the n times cap product beta to the n. Okay, this number is the degree of the polarization on each abelian variety, which are on the fiber. And by some miracle, this number is integral. Okay. And so the interesting thing is the following, is that this is important. So there is one important class of abelian varieties, which is a principally polarized abelian variety. This is the one that when you write down the polarization by Riemann-Hilbert, this you get just a bunch of 1. Okay. And so for A equal to 1, this is enough to guarantee that the fiber, pi, sorry, is a principally polarized abelian variety. So these are the simplest possible abelian variety that you can imagine. Okay. So again, let's go back. So I have this conjecture. I have a one class which I know it's the class from the pullback, expected pullback. If I have a fibration, then I expect another class. If it's projective, I expect another class. Okay, great. And so the theorem is that for the principal abelian case, this is fine. Okay, so this is the theorem. So the main theorem 1 says the following. So if I start with a Hyperkähler in dimension 4, okay, so it's a 4-dimensional example, this thing, and I assume the condition that I told you. So there exist algebraic classes. I will give you another form, which is alpha and beta in the Néron-Severi, but at the moment algebraic class is in Z, such that, so I want a condition of before. So I want alpha non-zero, I want alpha nef, and I want that the integral of x of alpha to the 4th is equal to 0. And for beta I want the following, that the integral over x of alpha square beta square times 1/2 is equal to 1, the smallest possible number. Then the conjecture holds. That's the theorem. Okay. So this means that if you expect to have a principal polarization, it actually does have a principal polarization. Okay. And so, okay, so great. So that's the first part. So at least in this situation, I know the conjecture is true. Now I can try to play the same argument as Scudder. Okay, so now I have this conjecture. Now I have to reply only question 2 that I had before. So can I use these to classify Hyperkähler? And the answer is yes. Okay, so under the same condition, I can say that the Hyperkähler is actually, they are all the same deformation type. Okay, and so how do I do that? Before doing that, let me take still a few minutes just to give you an example of Hyperkähler. I give you 2 examples that again I studied during, actually Claudius told me to look at during the undergraduate thesis, and they are the easiest example of Hyperkähler or somehow of systems, of integral systems coming from algebraic geometry, which are the Bouville-Mukai systems. Okay, so let me say that in just two lines. So let me go over here. I leave this theorem. So examples before showing the main theorem. So if I have a K3 surface, well, there are 2 examples that I can look at. The first one was, so how do I create something in higher dimension? This is non-trivial, but okay, the first thing you can do is the following. You can look at the sim2. So this is S times S, and then you mod out by the symmetric group sigma 2. So this comes with a symplectic form, which is unique. The only problem is that this thing is singular. Okay. The good thing is that it's not too singular. Okay. So the singularities here are the following: are somehow are cones parameterized by K3 surface. So the picture is the singular locus, if you want. So it's a bunch of points over so it's a whole K3 surface, but the singularity are just cones over there. Okay. And so we know very well how to resolve a cone. It's a quadratic cone, so I just blow it up. Okay. And in this case, actually it does work well. And so this is called the Hilbert square. So you can take the Hilbert square, which is a resolution of singularities. So here I have a cone, and the cone will become a small cylinder. Okay. And so this is the Hilbert square. And the nice part about this is that how do I see that this guy still keeps the symplectic form? Well, I can do a local computation, right? So this is again a first exercise in algebra geometry. So you take a cone. What is the cone is C2 modulo sigma 2. When you resolve it, this is the cotangent bundle of P1, which of course comes with the symplectic form. Okay, so locally this looks like T star of P1, in which you contract the zero section into C2 mod mu2. Okay, so that's the local picture. Okay, so that's the, and the interesting thing is that, okay, it's not done yet, but this is an example of Hyperkähler. So S2 is Hyperkähler compact. Okay, so that's a statement, and these can be generalized to an arbitrary number of points. Okay, and now from sigma 2 you can do two constructions. You can do here. The first thing you can do, okay, let's take a K3 surface, which is very special. So this is first example. And the second example, let's take so I showed you the quartic before. Now let's take a 2-to-1 cover of P2. Okay, so this is another example of Hyperkähler. So it's a cover which is a 2-to-1 map. It's not of everywhere. It's not a covering. So there is it's ramified, and it ramifies along a sextic curve. Okay, and there you can imagine the following construction. You take 2 points, okay, and then you map them into P2, and that gives you 2 points, except in some place. So what does it mean? It means that you take S2, and then what you do, you get naturally a map which is not everywhere defined over P2. Okay, and somehow by just taking, if you want to pay it dual, sorry. So how do I do? I just take the 2 points on the K3 surface. I take the image into P2, and then I take the line passing through that. Okay, so there's a unique line through 2 points, except in some cases. And so this is actually birational, so-called. So moduli space we call it M1, which comes with a Lagrangian fibration. Okay, so M1 is Hyperkähler of dimension 4 again. And by theorem of Huybrechts, this thing is actually deformation to the Hilbert scheme. Okay, so the key statement is that we want to prove that this is one of the example, or not quite, because this is not principally polarized. This is the correspond to do the following. You take curves, you take the Jacobian on these curves. This is genus 2 curves, so it becomes abelian surfaces. But is M1 somehow? So it's not. So M1 it's a relative peak 0 over curves which are hyperelliptic, such that so they come with a 2-to-1 map into a line. Okay, so what I can do then, I can do, instead of doing a relative peak 0, I can do the relative peak 1. Okay, so this comes again with a map into P2. Okay, so I call it pi, and this is a Lagrangian fibration again. These two are the example of Boville-Mukai system. It's Hyperkähler of dimension 4 again, and this time A is equal to 1 in this example. Okay, so this is an example of something which has two classes in which you have a principal polarization. Okay. And now, okay, great. So we have this example, and now we want to prove that this is the analog of the quartic in the theorem of Kodaira. Okay, so this is what we want to prove to be our case. And so that's the case. And so this is the formation to the Hilbert scheme. So let me say again. Again by theorem of Hyperkähler. Okay, and so theorem. Okay, so that's the second example. So this is main theorem 2, and this is actually the whole theorem. And so is that the Kodaira proof works. Okay, so this was conjectured by O'Grady. And so it says the following thing. So I take X, a Hyperkähler fourfold, and so this is let me call it O'Grady conjecture. And so it assume actually it's a strong version of this conjecture. So it's assume the following three things. So assume that there are two classes. I don't need to be algebraic in this case. This is just a general statement. So just two classes in cohomology such that the following properties holds that the integral of alpha to the 4 is equal to 0. And actually, I don't even need anything about beta. The only thing I need is that alpha square beta square is equal to by 1/2 is equal to 1. Okay, so that's exactly the situation as before, but I don't need to be neither algebraic, need nothing. Then X is a deformation equivalent to the example before, and so if you want to K32. So they are all deformation equivalent. Okay, so that's a theorem. Okay, and yeah, okay, so and that's how to that's a classification theorem. So in some sense, and how do you prove that? You just use a similar argument as so you take something which looks like this relative peak one. You use the fact that you make this class algebraic. You use the fact that then you have a Lagrangian vibration, and then you study very well this Lagrangian vibration to prove that actually it must be isomorphic, at least very general, to this example of Bouville-Mukai. Okay, so that's how the argument goes. And yeah, maybe I can even stop here actually. So if there are questions, at least I finish on time, or at least morally on time. If you want, I can say something more about the proof, or answer some question if you want. Yeah, let me stop here. At least we are on time. We are. Thank you.
Thank you very much, Emanuele.
Thank you.
Are there any questions?
Thank you, Emanuele, for this wonderful talk. Very interesting. And yes, I'm curious about the proof, or at least some details of the proof.
Yeah, okay, so the proof, it's actually there is a part which is nice and the part which is very the proof is very algebraic geometry somehow. So let me just say a few lines about it. Just really a few lines. So what is the idea? The idea is the following, is that well, we have to use everything that is known about Hyperkähler dimension 4. And so the first thing we need to know how, if you have a birational map, so an isomorphism only in an open subset, you want to know what is this locus of indeterminacy of this map. So that's the first result. And this is the result by Wierzba and Wisniewski, that says that if you have an Hyperkähler fourfold and you have a birational map into another Hyperkähler fourfold, then the indeterminacy locus, well, it's a composition of so-called Mukai flops. So if you take as small as possible indeterminacy locus, is a plane. So then the indeterminacy locus is a plane. So this is a result. It's a result about. It's a pure algebraic geometry result. It's about something about. You have a variety which you know being rationally connected. You have to prove it's really P2. Okay, so that's the first statement. Okay, so that's something that we use. The second thing, and this is the hardest part of the proof. So this we need to say something about the possible types. And so one thing that you can do is the following argument. So if you have a Lagrangian fibration into P2, let's say, okay, and you have a class, so you have two classes, alpha and beta. So alpha induces still as a Lagrangian fibration, and let's assume that you have another class beta with the property that the integral of beta 4 is equal to 0, and the integral of alpha square beta square is equal to 1. Then it's not so hard to prove that so beta will assume it will induce another map P prime, and so that's not possible. So this situation cannot be possible. And so if you think a second in the conjecture above, so what fails here? So the fails is that A alpha is supposed to be Nef. So the statement is that beta cannot be Nef. Okay, so you cannot have two Lagrangian fibrations such that one induces a principal polarization on the other. So that's some funny result, but it's in this case it's not so hard to prove this thing. And so the thing we have to prove such a result without knowing that we have a Lagrangian fibration. Okay, and so that's quite involved. And so how does it do? Well, it goes via somehow we prove the following statement, that it's either it does admit a Lagrangian fibration, and so the situation is impossible, or it does not, and then you have to study somehow. In some sense, it's a question of commutative algebra actually, but it's a very hard question. So you need to prove that this situation does not arise, and the way that we prove it that if it does not admit a Lagrangian fibration, then you have a morphism into something, and this something must be rationally connected. So you must have a morphism from your Hyperkähler into something in P5, and then you do a case-by-case analysis that was done by Voisin, and you prove that it cannot happen. So this is really a case-by-case analysis. So you have a Hyperkähler fourfold which maps into some hypersurface in P5 of degree smaller or equal than 12, and you have to prove that they are very singular, and you prove that each of these cases cannot arise. So the proof is not the cleanest, but it's really a classification proof. And then, okay, once you have these two things, then somehow, then it means that by these two results together, you conclude, let me just say one line. You conclude that the Nef cone, so the cone of Nef classes, if you take something very general, will be generated by our class alpha and some other class, which I call it D, and by result by Markman. Yes. This cannot be Nef, so it must induce a divisorial contraction into something singular. And then, okay, and then it's then we use some result again by Wierzba. So we really use everything possible that classifies this the singular locus, the exceptional locus of this map. So this is divisorial contraction. And so you classify, we need to prove something here, but essentially the exceptional locus has to be a P1 bundle over a K3 surface, S. So that's our K3 surface. And now, okay, now there is a small magic, which is it's a P1 bundle, so it's associated to a vector bundle of rank 2 on the K3 surface. And now the magic is that this vector bundle is stable, and it's the Mukai bundle, so it's rigid. Okay, so it's a rank 2 bundle on a K3 surface of degree 2, and so these two conditions by Mukai's theory, it's unique. Okay, and so this means that exceptional divisor, it's unique. And then you use some theory of relative Albanese varieties to show that X must be birational at least to the relative Albanese, but it's the same. And so this means that X has to be birational to our Bouville-Mukai example. Yeah, so that's a bit the strategy. Yeah, but we use everything possible together with a very hard classification of which Claire did in her paper. Yeah.
Do you think that the first conjecture? I mean, this is possible to classify?
Yeah, there are many conjectures that you can ask. Actually, that's a very good question. Actually, that's a key question. Actually, so some part of the proof, for example, this part is the most interesting because our proof is terribly bad in some sense, and so it would be nice to have a conceptual proof. So this is really a commutative algebra proof. You have some graded ring, which you know only the parts, the positive part, and you will want to prove it does not exist, this ring. So it's something very, very, very Yeah, it's a purely commutative algebra proof, but you cannot do algebraically, and so you have to do this proof, which is geometric, which is very involved. But in theory, it should be true in general, yes. So if you expect something to be a principal polarization on each fiber, then you do expect that this situation does not arise. That would be actually something that will. It's a consequence of the Strominger-Yalzheimer conjecture. So this should be true, but yeah, that's really interesting.
But it should be expected in any case, in any dimension you have just models.
Yeah. But not the proof. Okay, the proof won't go through in any dimension because there are examples in dimension 10, which is indeed a great example, where you have a principally polarized fibration, which is not of type. They're not all deformation equivalent. But it's something else that goes wrong. It's the last study. The last morphism is different than in higher dimension. In higher dimension will be something stratified and will be much more complicated. That's the thing. So there are other things which goes wrong, but this part actually, this should a priori go through somehow.
Maybe one can try also to modify, to relax the, or to modify, not to relax, the contrary, to rigidify the notion of deformation equivalence.
That's also possible. That's correct. Yeah, that's also possible. But at the moment we know nothing. Ah, sorry, I forgot that one other thing that we use here that is secretly here. It's I didn't say, but it's this theorem of Solomon. Sorry, that's important in our proof. And again, this we don't have it in a higher dimension. So in dimension 4, this theorem of Solomon does give you a possibility for these Betty numbers of a Hyperkähler. So the second Betty number can only be bigger or equal, smaller or equal than 23. Yes. And the condition that we have forces the Betty number to be 23. So that's something important, and this is not true in general. Somehow there is something about dimension 6, but the proof is wrong, I think. So it's still open somehow. Yeah. So that's another thing that we use in dimension 4. Yeah.
Emolo, a question.
Sure.
For these results of yours, for instance, your theorem 2, the last thing you spoke about.
Yeah.
They establish, in this in particular, establishes a sufficient condition for the result. But is this also necessary?
It is necessary, yeah. If you have some,
right, because once you have the structure, it's easy to construct alpha and beta, I guess.
Exactly. So once you know that, for example, yeah, okay. So there are two examples in dimension 4, right? So the first example is K32, and there, by the example of Ville-Mukai, this does satisfy that condition. Yeah. So that's the first thing. And the other example is Kummer 2. Kummer 2, they do not satisfy this condition, but they do satisfy this theorem with is not principally polarized, but it's a polarization of degree 3.
Okay.
And so then you can imagine that you can try to state a similar result, right? And so a posteriori, and then there is some general conjecture to say that these are the only two possibilities. And so you can try to say, oh, okay, that's it. Those are the only two, right? So it's either 1 or 3 or multiple of it. Multiples are of course possible.
Okay. Thanks.
But yeah, so but they are necessary. Yeah, it's an if and no if. Yeah.
Yeah, that's very nice. I mean, it's a full characterization.
That's more, yeah. It's but unfortunately, yeah, the proof for 3 actually it won't generalize in this case. You need something else there. You need some. I think you need some new idea even for a dimension 3 for degree 3. Yeah, and dimension 6 somehow. Yeah. Yeah.
Are there more questions or comments? So let's thank Emanuele for his
presentation.
Thank
you very much.
Yeah, this was. I hope.
See you.
Wait, we meet in Genova. Yes, that's fine. Yeah, that's absolutely.